How do you rotate a digital photo in place, with no extra space? Rotate image is a Pattern Mastery 100 favorite and a frequent question at Google, Amazon, and Facebook, designed to test your understanding of matrix manipulation. Over 35% of candidates either use extra space or get tangled in index math. Master this, and you'll ace matrix transformations in any interview. Let's break down rotate image using the basic approach, so you can confidently tackle any in-place matrix manipulation problem. Given an NXN 2D matrix representing an image, rotate the image by 90 degrees, clockwise, in place, i.e., don't use another matrix. Input. 2D list matrix, NXN integers output. The matrix is modified in place. Interviewer might ask, how would you rotate a digital image in place for real-time rendering? What's tricky? Must rotate in place, no extra space for another matrix. Need to move elements layer by layer, or use clever matrix transposition and row reversal. Index calculations for four-way swaps can trip you up. There are two classic approaches: transpose and reverse. Transpose the matrix, swap rows and columns. Reverse each row, layer by layer four-way swap. For each layer, move elements in groups of 4, rotating their positions. Let's clarify the transpose and reverse method. Transpose. For each cell, I, J, with I less than J, swap matrix IJ, and matrix JI. Reverse. For each row, reverse its elements. Transpose the matrix. For I in 0 to n1. For j in I plus 1 to n1. Swap matrix IJ, and matrix JI reverse each row. For each row in matrix, reverse row in place. Now, let's break down the first Python solution for rotate image, a clean two-step strategy that flips the matrix and then reverses it to achieve a perfect 90-degree rotation. We start by defining the solution class. LeetCode looks inside this class to find the rotate function to run. This defines our rotate method. It receives the matrix we want to rotate 90 degrees clockwise. We take the size of the matrix. Since this is an n times n square grid, n tells us how many rows and columns we have. We begin our first loop, iterating through each row index I. Inside that, we loop through each column index j, starting from I plus 1. This ensures we only visit the upper right triangle of the matrix, avoiding unnecessary swaps. Here's the key operation. We swap the element at row I, column j with the element at row j, column I. This operation transposes the matrix. It flips the matrix over its diagonal. Since we touch each pair once, this transpose step contributes to the O(n) squared time complexity. Now we start a second loop over each row. We reverse the entire row in place. Reversing each row after transposing gives us the final 90-degree clockwise rotation. And that's how this algorithm works. It first transposes the matrix to swap rows and columns, then reverses each row to finish the rotation. Efficient, simple, and elegant. Test case check. Let's walk through it. Input matrix equals 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's test our function using this input matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. You can think of this as a 3 times 3 image, where each number is a pixel value. First row, 1, 2, 3. Second row, 4, 5, 6. Third row, 7, 8, 9. Our job is to rotate this image 90 degrees clockwise, in place. Quick logic check. After a 90 degrees clockwise rotation, the original bottom row, 7, 8, 9, becomes the new left column, 7, 4, 1. The middle column forms 8, 5, 2. The original top row, 1, 2, 3, becomes the new right column, 9, 6, 3. So the rotated matrix should be 7, 4, 1, 8, 5, 2, 9, 6, 3. Output: 7, 4, 1, 8, 5, 2, 9, 6, 3. And that's exactly what our program outputs: 7, 4, 1, 8, 5, 2, 9, 6, 3. It matches the expected result perfectly, which confirms that our in-place rotation logic is doing the right thing. So, our implementation is correct. The algorithm successfully rotates the matrix 90 degrees clockwise without using extra space, efficient and accurate. We begin by defining the solution class. This is the structure where LeetCode reads our rotate method from. This defines our function. It receives an n times n matrix and rotates it 90 degrees clockwise in place, meaning we must modify the original matrix without creating a new one. We store the size of the matrix, n. Because the input is always a square matrix, n gives us both the number of rows and the number of columns. We begin looping through each layer of the matrix. Think of the matrix like an onion. It has layers that we rotate one at a time. n/2 ensures we cover only the outer half, because rotating an outer layer also moves the inner layer. Inside each layer, we loop across the elements in that layer. J moves from the start of the layer to the end of that layer, avoiding corners being rotated more than once. We temporarily store the top left cell of the current rotation cycle. This is the first step of our four-way swap. We take the value from the left column and move it to the top row. This starts the clockwise rotation. Next, we take a value from the bottom row and move it into the left column. Now we move the right column value down into the bottom row spot. Line highlighted, matrix Jn, 1, I, equals temp. Finally, we place the original top left value, stored in temp, into the right column. This completes one full four-way rotation of the cycle. And that's how this algorithm works. It first identifies each layer of the matrix, then performs a four-way swap for every element in that layer to perform an in-place 90-degree rotation. Efficient, simple, and elegant. Let's test our function using this input. 5, 1, 9, 11, 2, 4, 8, 10, 13, 3, 6, 7, 15, 14, 12, 16. These numbers represent a 4 times 4 matrix, which you can think of like a square image or grid of values that we want to rotate 90 degrees clockwise. Here's why the solution works. The algorithm rotates the matrix in place so that the first column from the bottom becomes the first row in the new matrix. The next column from the bottom becomes the second row, and so on. For example, the original first column, top to bottom, is 5, 2, 13, 15. After rotation, these appear reversed as the top row, 15, 13, 2, 5. The original second column is 1, 4, 3, 14. After rotation, it becomes the second row, 14, 3, 4, 1. The original third column, 9, 8, 6, 12, becomes 12, 6, 8, 9. And the original fourth column, 11, 10, 7, 16, becomes 16, 7, 10, 11. So, the fully rotated matrix is 15, 13, 2, 5, 14, 3, 4, 1, 12, 6, 8, 9, 16, 7, 10, 11. And that's exactly what our program outputs. 15, 13, 2, 5, 14, 3, 4, 1, 12, 6, 8, 9, 16, 7, 10, 11. This confirms that our code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully rotates the entire matrix 90 degrees clockwise in place, efficient, accurate, and reliable. So, let's wrap it up. The rotate image problem is one of those elegant matrix challenges that looks simple but quickly exposes whether you really understand in-place transformations. No shortcuts, no extra space. We started by restating the goal. Rotate an n by n matrix 90 degrees clockwise, directly in place. It's about repositioning every element exactly where it belongs, just like rotating a digital photo pixel by pixel, without creating a new copy. We compared two main strategies, the transpose and reverse method versus the layer-by-layer four-way swap. Both work, but the transpose and reverse approach is simpler, cleaner, and easier to explain in interviews. The key challenge? Managing indices correctly while staying truly in place. Our plan was straightforward. First transpose the matrix by swapping rows and columns, then reverse each row to complete the 90 degrees rotation. 2 simple passes, 0 extra space. We followed that logic precisely, ran the code on LeetCode, and it executed successfully. No errors, no extra memory used. We verified the results, and every test case passed exactly as expected, confirming that our rotation logic holds up perfectly for all matrix sizes. The big takeaway? Mastering in-place transformations like this builds your confidence with array and matrix manipulation, a skill that's essential not just for interviews, but for real-world data and graphics processing challenges.